And yes, we are back. Let's get started, even though we are quite limited numbers in presence here. Okay, well, anyway, this is the Software Engineering Methods, lecture 10. As you probably saw, last week's lecture was the lecture 2 weeks ago was given as an online lecture because I was unable to be present here to give the lecture. And last week was cancelled also because of research-related absence. So you have had a couple of weeks now, during which we haven't had any new material or new stuff to talk about. Although for project 2, the project segments or parts have been introduced as per schedule. There's now 3 parts out of 5 given on the course web pages. They talk about use cases, use case diagram, use case descriptions, design of user interface, and deployment. Basically, the idea is that the last 2 segments include things like activity diagrams and some packaging documentation, so that after the project is done, you will have software architecture documentation for software architecture for the media distribution system that the Fun TV case represents. There's also an example project output on the Noppa pages. Scroll down to the very bottom of the project 2 subpage. There's an example output or example documentation from course held 2011. That case was different, and there's some changes here and there, but the main idea is the same, and that work is a good example on what sort of work, what sort of things you are tasked to create on the project work. Of course, that also means that because I know what's in the example, you shouldn't directly copy-paste it on your work, but use the ideas, or at least look for example in different diagrams or representation of your own data for your own work. Okay, so last time we had lecture, the online lecture, we talked about software architecture. The software architecture is specifically what it means, what it actually is, what's included in software architecture, and why it's wise thing to have one, or why in general anyone wants to have software architecture. The analog for designing a architecture for software in the lecture was in terms of creating buildings. Of course, the idea is the same. If we have software architecture, we want to define our system from some viewpoint. If it's network or deployment or modules or work divisioning or schedules or whatever, we can have different sorts of architecture views on the system what we want to build. Similarly, with buildings, we have sewering plan, electricity plan, floor plan, all these other things, rescue plans, in which the people building buildings can actually know where the doors are, where the windows are, in what order should we install things like ornamental glass walls and stuff like that. Have a good idea on how to build the building, and also how to schedule different things to be done, or manage different outsourced resources like subcontractors and stuff like that. So basically the idea with software architecture is completely the same. We are doing different sorts of definitions or different sorts of views on what the software should be doing or how it should be created, so that we can manage things, we can design things, we can even sometimes test things before we have something that functions. With software architecture, it's actually more important, since unlike buildings, there's no intuition in software development. We kind of expect with buildings that for every room there should be at least one door or passageway, possibly some windows. Well, this room doesn't have any, but still, and also floor and ceiling. It should be walled from all the sides. So basically, if there's something really badly wrong or missing, it's easy to see if we are building or creating buildings. But with software, we can't actually see them. We can use electron microscope to look into the hard drive, and we might see some, well, even some atoms or stuff like that, but still we are unable to see the software. And since software can basically be created any way we design it, there might be things missing that we aren't actually even thinking about before we have the entire system. And if we are doing large software or large service, then we are in trouble if this major problem comes apparent only when we are launching the product. So that's the architecture's idea. Of course, there's a wealth of different things mentioned why it's important. Of course, well, the increase in distribution, increase in integration. So basically, it means that there's more people using our software. It's present in more places, and it's connected to wealth of different things. If we want to create something simple, or well, something fairly common like internet service for some shop, or create a custom store in the internet, we have to use at least several, if not tens or over 100 different services simply to get our system working. And also the different systems which are using our software. Terminals, user interfaces, a bit old words, basically meaning platforms and different devices which can connect to different sorts of services. Of course, purely web service, Windows stuff, desktop computers, Android systems, Apple products, all these different things and different technologies used to implement them mean that we are, living in an age where we have several components, hundreds, thousands actually, of different technologies which may allow us to implement all sorts of things, but we still have to get these things to talk with each other. And that's the architecture there. Design so that we know how systems should behave before we actually implement it. And that gives us not only the first set of rules based on which we can start to develop the software, it gives us also the rules based on which we might want to test the software later on. Okay, so considering what goes into architecture and how this all ties into the topics of this course, this document template is simply the software architecture document template from the Rational Unified Process. It gives an idea on what sort of things there should be on defined architecture. This, as you may see, it's several things. Actually, there's more details there than probably is present in real life when someone starts to implement something. I'm not saying that the architecture design is something that everyone does. So of course it's not. If we are doing something simple like creating first demo version of a game, or creating a small service, or basically doing just something like a tool for internal use to manage version control or stuff like that, it's actually completely possible that none of this stuff is ever thought out of or even talked about. But still, the Russian Unified Process basically says that if we want to create fully working architecture, we have to have these sort of things. And these things, for example, logical views, use case views, deployment, implementation, data view, basically saying what sort of databases, what sort of data the system should handle, are all really nice things. They go into details, and they are all part of the design part of the software development. At the varying, with varying degrees of design, we can start implementation, and with varying levels of implementation, we can start testing, and the waterfall, well, kind of approach takes care of the rest. If we have something that we have designed, we probably can implement it, and if we can implement it, we can test it, and then we have a software product. So, what I wanted to talk about today is actually going one step towards actually doing programming. I'm not going to talk about the different aspects of object-oriented programming or stuff like that. That I covered about a month ago in a lecture where we talked about different attributes and methods and ways the different objects communicate with each other. This lecture, or the topic of this lecture, talks about going from the use cases towards actual program code. So basically means that we talk about use case analysis. Of course, the analysis and design, well, the analysis in rational process means that we try to understand the problem, and the design is the other side of the same coin, trying to design the solution for the problem. So basically, the idea that trying to get from the requirements all the necessary parts and then create software architecture which fulfills all the needed things. You also should keep in mind that planning and design isn't actually completely the same thing. We talk about design when we create software. We talk about planning when we talk about more general stuff like management of the project and planning schedules or shifts or milestones or stuff like that. But the software is always designed. Also in some documentation, some books, perhaps there's a significance here. But anyway, the idea is that the requirements, the use cases, all the different things we have identified, the need for different activities. For example, with the ATM machine, we have use cases of withdraw money, ask PIN code, print receipt, load money on the e-card, these sort of things. How these can be used to make the actual design. So, and obviously, in addition of making the design, how it can be somewhat solid, reliable, and how we can use our existing work to help us here. The documentation isn't done simply because I told you so, because there's a lecturer saying that you have to create this and this documentation, and when you have done that, then you create something else. No, it's because we want to start with small steps. First, take the general data, compress it into actors and use cases, and from those use cases, design classes and class diagram, and based on those abstract class diagrams, start to take more focus on the actual things that can be programmed. So, what we want to have on the analysis and design is, things we have been doing on the project work already. Use case model, the requirements documentation, and some sort of sketch for architecture. Basically, these, from the viewpoint of the project, can be said, these are the the use case model is the part one of the project work. It's simply just identification of actors and different important things. The requirements documentation, the other requirements, basically that's more or less the case description. Of course, if we would be doing this in real life, you would have to interview people, collect information, make sure that your technical infrastructure actually supports the amount of people you want to have on your system. And possible sketch for architecture. This coming from the case description. For example, in our project work, there's several subsystems with the Fun Media Corporation, like warehouse system or sales database or customer database. And we want to create something that fits that existing architecture, existing network of different services. So of course our initial sketch for the FunTV architecture would be something like a separate module or separate service running in the same network but using the same services or databases or data warehouses or whatever you want to call them as other services. So, so what we want to have when we are done with the design analysis? Of course, the design model, actually this means something that's implementable by programming or something that's close enough that the programmers can or developers can start doing the work. The architecture documentation, the document, this meaning that there's an actual approved or initially approved sound plan on how to get the software created or what sort of software to create, and there's a data model for databases and other implementation, meaning that we have sort of an idea on what sort of messages the different objects, for example, exchange, what sort of interfaces there are within the system, what sort of data is collected, saved, and used. For example, this may seem that it's kind of an irrelevant thing. It's obvious that, okay, well, the database handles or saves whatever we actually want to put there. But if we are creating a larger system, we of course need to have the different tables and names and attributes and things like variables which can be saved on the database known so that we can do parallel development. For example, develop several modules at the same time, or like actually on yesterday's exercises there was a question on the possibility for unregistered users to order things from the web store in the case description. So if we want to allow that, then we would have to, of course, collect the contact information or have some sort of way to recognize what was sent where. So these sort of all are related to data. What we have to collect, what we have to save, what we have to know about the user so that we can allow certain things. So these all are things that just have to exist and someone has to make the decision on these things. So we basically are here. The idea is that by doing the analysis, we get close enough to the actual construction, or basically we get over the line of the construction so that we can do implementation and start do testing. So the other picture I want to show at this point is this. So the rational process approaches the development of software this way. We first start with the use cases and the free-form documentation. We create the analysis classes, which are basically something taken out from the use cases, the actors, the data models, the interaction of different classes, class diagrams. Then go to design more concrete things like activity diagrams, sequence diagrams, making actual components and designing how different modules exchange information, how certain use cases actually do their work. So now we are talking about the design classes here. Then basically this design is implemented as source code, and when we test and compile that this thing works as designed, as planned, then we have executable code and we can start the deployment. So I'm not saying that it's not just trivial step. I'm saying that there's a couple of ways to make it actually easier than it has to be. Here there's some description of things we want to, what we have to do in the design and analysis workflow. So, use case analysis, class design, all things we are already doing, and the idea is that by extracting info from the use cases, we can make the deployment diagram like we are doing in the project 2. The deployment, of course, says that where the physically different things exist. Also define things for logical view, process view, and implementation view. So basically, from the end user functionality, extract all these different things. Yes, so the use cases are the starting point of the analysis. The interaction between objects is something that leads to class diagram. This is something you already know. So I have to skip ahead a bit because yes, it's coming next. So basically, the use case is directly involved in creation of class diagrams, sequence diagrams, and communication diagrams. So the exercise a couple of weeks ago in lectures were the written description of use case using verbs and nouns as different messages, activities, or actors is now transformed into these 3 different diagrams. And when we have the classes, we can basically do the identify the boundary, control, and entity classes. This BCE model is actually really let's say crude but efficient way of creating or defining different functionalities for classes. So when we have, we of course need to have the interface, the user interface, which collects the information or show information on the screen. We also need to have certain functionalities, and we also have to save certain data because at this point we should have some sort of an idea of what sort of data we are trying to handle, what sort of activities we have, and what sort of actors we have, so what sort of information our system will collect and what sort of views our system is supposed to show. So, the analysis classes are really simplified way of doing this. We have a boundary class which handles all the information exchange between actors and, it also meaning that between systems or modules. We have control class, which actually is the heavy lifting part of the software, doing all the actual work, or at least at the start of the analysis, handles all the data manipulation or calculations or activities. And there's entity classes, which are more or less used to handle data transactions from database to database, these sort of things. So basically, meaning that everything can be divided to three sorts of classes. The boundary classes, these are these represent different things like user interfaces or network interfaces or hardware interfaces, view or window on your desktop computer, application view on your mobile phone, your printer, your barcode reader, whatever exchanges information between actor or user in this case and the system itself. So the boundary object is the object that gets signals from users, other systems and hardware and delivers them forward. It's also the one that shows stuff. So if we consider what could be is something like a graphical user interface library, like tkinter for Python programming language, is something that probably would be really close to boundary class or user interface in general. So what it actually means is that there's boundary class. It's on the class diagram. Any of these notations will do. The boundary class uses this shorthand symbol here. So basically that means that we have boundary here, let's say it's user interface, and we have actor who's connected to the boundary class. So basically not really nothing really complicated. We have user interface class, which is responsible on our design on collecting information from the user and showing information to user. We can also add another boundary here. Let's put here network adapter is another boundary class. Let's connect that to let's say it's an administration database. So there's actually now there's two connections. The administration database is connected to network adapter, class handling all the network traffic, And we have user interface class, which is connected to the user or the person using the software. And like mentioned on the slides, usually there's only one on this first step of analysis. There's only one boundary for each different actor. That also means that, well, later on these analysis classes will live a bit to make the system more, well, realistic. But we have to start from somewhere. So now that we have the interface, we have boundaries, we have way to collect and show information, we need control class. Control class, like I said, is the so-called heavy lifter of the classes. It's the one which implements all the events or activities. It controls and coordinates what the system is doing. It handles all the cases or transactions and things like that. It also means that the control class is usually the most complex part of the first system, but interestingly enough, it's also the one class that usually tends to just disappear as the design matures. That's because these different activities and things are usually included in other classes. But the control class starts the design. So it's basically, well, the programming part. And it's represented with the circle symbol with arrow in it. So if we want to add a control class here, we can just make an, well, let's start with 1. And we can say it's an, well, input validation. So basically, this is connected here. So what it means is that we have a class which is responsible for user interface, and it forwards the information to control class called input validation. This input validation class is responsible for checking out, first of all, that all the required fields are present, that the inputs are sane. For example, no one has said that they are 300 years old. Okay, well, if we design software service for vampires, then maybe. But otherwise, no. That everyone has given address, that the address is something that's actually valid, these sort of things. So all these things go to the control class. We can also add another control class here. So let's say this one's traffic control. I apologize for my handwriting, but, well, try to live with it. The traffic control class here handles the network adapter, and it's, well, its main functionality could be something like, well, verifying that all the data is present, the sent data or received data isn't corrupted. There's every message is signed or handles the secure connections, opens, closes connections to different systems, handles the handles of network traffic, all the different things that are needed for this software, or well, this thing to actually well, do things. Similarly, well, let's add one more. Let's not give it any connection yet, but let's put 1/3 control class here. data manager. So if we want to retrieve data or browse things that have been input or basically anything, then we can use services from that system. So we can design that, okay, the inputs are validated, input validation and input control is done through the input validation. The network code, network traffic is handled through traffic control, and there's a data manager which handles all the other things like retrieving data or seeing how data is collected. So now only thing we are actually missing here is the entity class. The entity class represents the data or the management of the data. It's more or less the database or the tables in database. And it's actually, on that sense, it's really close to the actual implementation. Because if we already know what sort of data we want to collect, then we define entity classes which just summarize the information. So the entities, they are sort of independent. They mainly just handle the saving or, well, deleting data from their own system. They are sort of shorthands for databases which will be added later. So, well, on this example, we could add a couple of databases like user data, order data, or even something like, well, price data. These are just three different classes which represent all the data related to users, all the data related to orders, all the data related to price, or, well, in this case actually something that could make more sense is item data. So basically all the things that we aren't users, orders, but are items. So these three classes include all that. And their methods might be something like add user, retrieve user, edit user, all these, well, quite normal database activities. So, what we have after all these different classes have been identified is, well, it's called the view of participating classes diagram. It's nothing really different than just list of all the classes we have designed for this system. So considering the example in the slides, we have our form, we have our input control, project management interface, different sorts of entities, employees, projects, and our forms. We have, well, 6 participating classes, and these 6 classes should include all the activities, handle all the data, handle all the message exchange between user and the system. So we are sort of in the ballpark of actually implementing this thing. We know that we are mainly looking at 6 different parts. Of course, these things will live or change during the implementation, but basically we have a couple of interfaces, one module which handles all the work, and 3 modules which handle the data collection. On the example here, we have a bit similar situation. We have basically 3 control classes but otherwise we are in the same situation. So what I'm adding here is connections between the classes. This is just something I'll add. This basically starts to look a bit like class diagram. There's different types of classes with different types of stereotypes, the boundary entity control. There's also this starts to look a bit messy, but the blue doesn't have any special implications. It's just to avoid making the thing look like a spider's web. But anyway, it starts to look a bit like class diagram, and actually that's because it is a class diagram. If we want to expand on this, then we start to add different messages, different methods, different attributes into this, and that's actually the next step from this example forward. So now that we have the participating classes, user interface, network adapter, data manager, input validation, traffic control, and the entities, then we need to think about the object interaction. So this comes from the use case description. In this slide example, we are creating the first version of the input hours use case or system which can input hours. So this is the flow of events from that use case. So to make the object interaction work, we have to see what sort of interaction there actually is and create a sequence diagram out of the written textual expression. Of course, in this design of sequence diagrams, it helps if we have some experience on making source code or programming or doing development. But basically all these different activities, the system opens our form, system fetches through the project management interface, the projects that are currently open and puts them in the project list, so on and so on, basically gives us the notes on what information has to be sent. And since we have already identified the interfaces, the control thingies, and the entities, then it's just the work of adapting the written flow of events to the sequence diagram by using the PCE analysis classes. So starting from the use cases, and we actually now have a sequence diagram which has the different types of messages we have to send, and we have already identified the different modules or objects which have to send these messages or, handle these messages. So about the sequence diagram itself. This may be somewhat returning to the already told things, but the timeline goes from up to downwards. It's actually on the UML1, it was the only diagram which in any way expressed timing information. Of course, with UML2, that doesn't anymore hold true because there's the timing chart. But in the sequence diagram, the idea is to show on which order things happen. This is important, for example, when we want to design something some system where client and server exchange information. It also means that the programmer can look at the sequence diagram and know at what point their system is waiting for return call or returning message from server, and possibly even get the idea on how long should it take, so they can create timeouts and or possibly try to resend the information. But in any case, all the arrows here mean that this object sends message to another object. And for example, like in this arrow or message 11, it doesn't always have to be the object right next to the other one. They can actually skip over these lines. For example, here the employee opens from the main form the hour form, and then later actually just saves the information of the hour form. But the sequence diagram shows in which order the things happen. It also allows us to have self-checks like here, some iteration or calling itself, these sort of things. So what we want to present is a scenario from all the use cases, or in the case of project 2, on the relevant use cases. These are the use cases your group should be making or implementing in detail. The sequence diagram has a scenario. It's usually the happy path of flow of events, meaning that the happy path was the case where the use case happens with minimal amounts of problems. Basically, the sequence diagram should implement the same, and if there's some really important or really different activities or reactions to problems like server not answering or user inputting the wrong password 3 times, then that's represented in different sequence diagram. That's actually because the sequence diagrams have difficulties representing iteration and conditions, although there is possibility, there is notation for having conditions if else, conditions meaning if else things in sequence diagrams, but usually adding those alternative scenarios in one diagram is a bit of a bad idea because it tends to make the diagram really complicated. Okay, so that's one thing. The other thing we might want to create is the communication diagram. This is basically the same information, but with different notation. It just gives the idea of basically on using the class diagram, sort of a hybrid between sequence diagram and class diagram and use case diagram. It shows the different classes or different objects which participate in one use case. It also gives the order of activities, and at least in this point it becomes apparent that what objects have to be able to communicate with each other. If we create communication diagram, then at least at this point we know, for example, things like visibility boundaries. The visibility is really important thing in programming work. For example, which objects can call each other, which things in objects are private, public, protected, these sort of things. So at least in this point we actually see which objects call each other, which objects have to have connection to each other, and which objects have to be aware of each other. We also know the direction of information here. We know, for example, in this case, we have the hour form, hour form boundary at the middle, up in the middle in the diagram. We know from this that the employee, the main form, and the hour form itself sends information to that object. So if we would be doing testing or making changes to the hour form, then we would also know that we have to check the main form and the parts of the hour form which call the form itself, to ensure that our changes aren't breaking anything in the new version. Of course, the employee also sends, the actor also sends stuff, but the actor part is person just ordering the system to save state or save data. So we can be quite assured that the message there, the message 11, is actually just user pressing a button or save or something like that. But also, it means that the save message has to work, or there has to be a button for employee to press. Okay, so the communication diagrams, the different things are objects, and the objects are based on the classes. Like I said, these different links mean that there has to be visibility, and the sequence diagrams and communication diagrams are all almost the same. Of course, the communication, the sequence diagrams are better if we want to have, for example, show protocol or something like that. The communication diagram is more suitable, for example, in parallel activities. If we want to, for example, have two different things happening at the same time, then the communication diagram is more suited to that. But if we want to have really close details on how some activity happens, like transaction between the ATM and bank front end, then we want to use sequence diagrams. Okay, so like here, which actually is the example, we have customer, we have ATM network, basically meaning the bank, and we have different parts here. Display, keypad, card reader, of course these things are boundaries. The card validator, session manager, authenticator, these are control classes. And the ATM network is also a boundary between the bank network and the ATM system. So in this case, the different types of classes isn't represented, but it's really easy to, not guess, but to see which is what, which is which. The customer uses card reader, customer uses display, customer uses keypad, and there are several separate class handling the network traffic. So of course those are boundaries. The card validator, the session manager, and authenticator, they are things that actually do something in the system. So they are control classes, and since there's not a separate class which stores the user information because it comes from the network, then we don't have entities in this example. They are they come from the network. This also would mean that if we would be using this approach to design software, then we could see already that there's no local database involved here, or if it is, then it's used for some small things, and we don't have to worry about that problem. So, like said, the sequence diagram illustrates the events and the order in time, and complex operations, algorithms. Communication diagram illustrates the links between objects, messages in the network of objects, and it's more or less brainstorming and free form. Okay, so going back the slide I showed earlier, here the slides I showed earlier. From the use cases, we now have the analysis classes here. We have different stereotypes, different classes or different ways to divide the functionalities of the system to certain things. We also have some designs for components, some designs for message exchange, what sort of data we have to save in the system. And we basically already are here, since we had to do the sequence diagrams, we have communications diagrams, and actually we also have class diagrams which are derived from the use case descriptions. And if we add these different BCE stereotypes to the classes, or redesign the class diagram so that it applies these stereotypes of boundaries, controls, and entities, we are already half point there, making a design that's actually implementable by programming code. So, what else? Well, now that we start to have a group of diagrams, huge amounts of different diagrams, sequence, communication, class design, domain models, user interface designs, BCE models, that sort of things. It also would be really good time to start using packages. The package diagram is not very difficult thing. Basically, on some software design tools, like with rational rows, from which this screen capture is taken, actually for every use case, the system defines or creates a separate package or package and it means that the packages in UML, they are just folders in your project, which includes all the things which are related. So, for example, with the ATM example or this example, all the different versions of the diagrams, all the different diagrams, written text would go to one package, and then, everything would be neatly in one place for one programmer to find. Okay, so how many interaction diagrams then would you need? Of course, the ATM machine, or even simple thing like inputting your PIN code and validating that you actually are the owner of the credit card may mean that there's actually several different alternative flows. For example, everything goes correctly, or that there's no money in the account, there's no connection to bank, there's the PIN code is incorrect, or that the card reader isn't functioning, or that the system has run out of bills, or different things. Basically, with a fairly simple use case, you can come up with 5, 6, even 10 different cases or different outcomes for one thing. So the question is how many interaction diagrams you need, and I'd say like this slide here says, well, as many as you think you need. All the important or the really distinct different paths should be documented. But like I said earlier, keep in mind that with UML design, with different diagrams, with different documentations, the madness lies in making document out of everything. You can fill a library with documentation of one fairly simple software product if you were to do all the documents and all the details with the UML. So when you are designing interaction diagrams or communication diagrams, sequence diagrams, class models, PCE models, whatever, take into account the important things and supplement it with text. This line here, to convey all of the necessary knowledge to all of the stakeholders with minimal amount of excess data, is actually quite nice. It's so try to get your idea through with minimal amount of overhead, so that if someone else is looking for answer, like how many milliseconds should we wait, how many messages does this transaction take, or what objects are involved in this use case. Try to use of course, give all the information, but let the alternative things or possible problems be in the separate documentation. Because nothing is less usable than documentation which is full of details and things that are outdated and has unnecessary things mentioned there. Of course, the details are sometimes good, but keep in mind that if you add excess amount of details to your documentation, you also have to maintain your documentation, and that actually may take even more time than doing the actual implementation. So, what were the participating classes? The participating classes are, simple enough. They are all the classes which we have identified based on the PCE analysis. So when you are going through the slides set at home or for exam, keep in mind that the view of participating classes has nothing else. It's nothing else than just a list of things that are involved. If we have the line between them or message between them, it means that there's always some interaction, and it also means that they may exchange information, like here. Also, the idea that the BCE model is actually a class diagram. On this form, it looks simple enough. We have boundaries, we have control class, we have entities, we have data exchange between these things. But actually, what we are showing is something like this. If we expand the BCE model fully and we add all the message information from sequence diagrams and communication diagrams, we already are rather close to actually having something usable in development work. We have sort of requirements for what sort of things the boundary classes should have, what sort of forms, what sort of information they should gather. We have on the entities, we have a list of different database operations or data fetching operations. And in the control class, we have a list of different activities and what sort of, orchestrated events or controlled events we should be able to do with the entities and boundaries connected to that one control class. And, there you have it. So, that's the first step from the use cases and the different written descriptions and user interface towards making something that actually works. So, based on the domain model, based on the use cases, definition of boundary, control, and entity classes, how they should communicate with each other by taking the things from the use cases, the use case flow of events, then designing things like what sort of data the entities have to handle, what sort of user interfaces, boundaries our system has, and with the messages in how the different sequences happen for different use cases, how the communication between different modules happens. So, with that information, we are quite close to actual development. Now the only thing basically left to do is make the more detailed design. For example, for store hours, make a database, create the database, tables, make the decision on in what form will the data be fetched from the hour form and forwarded to the employee entity so that the employee entity can physically save it into the database. Or get personal information, how the actual message is created so that it fetches from the MySQL database the relevant information and how it should be parsed so that the boundary hour form can show it on screen in the form or window which is reserved for showing the hour data. Okay, I guess that's enough for this week. I ran out of slides, and I guess based on the reactions from the audience, that's not a bad thing today. So, thank you, and let's see